Chapter 28, Problem 10. Again, that one doesn't exist. This one is about a concave lens. And writing this down reminds me that on the last problem I did mention there was a convex lens, and you did see it in the applet, but I forgot to write it down. Okay, so this one is about a concave lens. I use the same applet, so here it is. Again, I'm going to put a candle here. I'm going to put the candle at a position of 100 and actually 200 millimeters away. Remember that I put the lens at 300 millimeters. That's kind of in the middle of the screen. So the object is 200 millimeters away. The image here is on the same side. That's because it's a virtual image and it's a concave lens, so we're not going to get a projection. You have to look through the lens in order to see the image, and it is a smaller size image. And here we have a position of 67 millimeters away from the lens. Again, you see that at the bottom. So we have 200 millimeters here and 67 millimeters here for the image distance. There we go. Okay, so DO equals 200 millimeters. DI equals 67 millimeters, but because it's on the same side, we have to introduce a negative here. The image distance on a concave lens is always considered to be negative, and it makes sense. If we left that out, we would come up in our calculation with a positive focal length, which would indicate a convex lens, and that's not the case, so we actually need that negative. You'll see that in a moment. So the equation is the same. 1 over f equals 1 over dO plus 1 over di, and plugging in numbers, it's going to be 1 over 200 millimeters plus 1 over negative 67 millimeters. And so again, on the graphing calculator, I'm going to do the right hand side, and then I still need to invert that number. So 1 over 200 plus 1 over negative 67. Then it comes out to negative 0.0099. Very small number that tells me right away that I'm not done. I still have to invert that number. And that comes out to negative 100.75 rounded negative 101, or because I have two significant figures, rounded to the nearest 10, which would be 100. So negative 100 millimeter. I underline the first two here because both of these are significant. So it's not rounded from 85, but it's rounded from at least 95 up or 104 down. It's hard to tell when you have these trailing zeros. This negative here means concave lens. On the last problem that I showed with the virtual image, that distance actually in reality would have to be for the virtual image would have to be estimated, because you really can't project it, so you can't really put a meter stick on it. So in order to really measure the focal length of a concave lens, you would have to put the two into combination, and it would look as follows. So here we have a concave lens, the same concave lens as we used before, and the same convex lens as we used before, and we put them as closely as possible. And then again we put an object here, and in order to get a pretty good measurement, I tried to put the candle as far away as I could, so to a position of 5, which means 295 away from the middle. Maybe actually the middle is at 311 of the two lenses, so 311 minus 5 is 306, and then the image is at 426 minus the 311 is 115, so I have 306 and 115. Notice there's the virtual image here from the concave lens, and that then becomes a real image here through the second lens, and there it is. So we have these two numbers. DO equals 306 millimeters, and the I, and this is a real image, is 115 millimeters. And we do the same calculation. And we're going to come up with 1/306 plus 1/115, and we need to invert that. That comes out to around 84, and I have to amend this just slightly. This one is the focal length of the combination of the two. So again, I believe that was 84 millimeters. But now, what we do with this number is we actually figure out the focal length of the concave lens. Again, because I said the previous problem, number 10, you really can't do that. But this is the way I do it in the lab, and you do the two. You combine the two, and then the equation for the combination is going to be really similar to our thin lens equation, as long as the two are sufficiently close to each other. And that's the way I would write it. 1/focal length of combination is 1/focal length of the convex lens plus 1/focal length of the concave lens. It's the latter that we need to figure out, so 1/focal length of the concave lens equals this, and now I need to get 1/focal length on the other side of the convex lens, so I get that. And now I'm going to use the 84 millimeters that we just determined minus the 50 millimeters that we determined in the previous problem, and then on the graphing calculator, or in any calculator, we're going to do 1/84 minus 1/50. Invert that, comes out to 124 millimeters, and the negative, I think you saw that negative, minus 124 millimeters, and that is within some error relatively close to the 100 millimeters for the concave lens. The reason why it's somewhat off is that the two are not in the same place. They can't be, so it's hard to determine a middle point between the two. Technically they should be in the same place, but of course they can't, so that's why we're slightly off, about 20% error.